Welcome to today's tutorial. Let's get started. Let's have a look at our agenda for today. Today we're looking at using the XLEe as remote I/O. First we'll look at why you would use the XLEe as remote I/O, and we'll also talk about PLCs and controllers that can be used with the XLEe as remote I/O. We'll talk about the steps required to program or configure the XLEe as remote I/O. Then we'll have demonstrations showing you a quick and simple setup if you just want to get the project done fast, as well as a more comprehensive setup. So why would you use the XLEe as remote I/O? The XLEe offers a mix of I/O that's roughly equivalent to several I/O modules or even a small rack of remote or expansion I/O. With the XLEe you have anywhere from 22 to 42 I/O points, you have DC or relay outputs to choose from, and you have both digital and analog points in every model that's available. You also have high-speed counting options, high-speed output options, and temperature sensor options such as RTDs and thermocouples. So it has a lot of compelling I/O options available. Next, we'll talk about the different options you have to connect from an XLEe. With an XLEe, you can interface with an ever-growing list of third-party PLCs and controllers. For an application that involves CAN open, the XLEe works great with that. Then, if you need to interface with Rockwell, you have Ethernet IP built in. With Modicon PLCs, Modbus TCP is available. For Emerson and GE products, Global Data is a native Emerson and GE protocol that's available in the OCS. Really, any modern PLC or controller is going to support Modbus TCP, which can be the default way that you interface with a lot of these third-party controllers. Then, when you need to interface with Horner OCS, C-SCAN protocol, and Ethernet Global Data are good choices. Another thing to note is that the XLEe is completely suited for DIN rail mounting. Most of the time when installing expansion I/O, you're almost always installing onto a DIN rail, and the XLEe, along with our other quarter DIN controllers, the XLT and the XL4, are designed with an integrated DIN rail mount. So that's another reason why the XLEe can work great as a remote I/O block. Now let's talk about the screen. The XLEe has a basic user interface. It's not designed with a color touchscreen, so in some applications as a controller it can be limited. However, as a remote I/O block, the XLEe screen offers far more user feedback and status than your typical I/O block, which usually just has LEDs for I/O status, network status, connection status, etc. So with the XLEe, you can very easily create your own custom screens to provide I/O status for both digital and analog I/O, as well as high-speed counting. Now let's talk about the steps that are required to program the XLEe as a remote I/O block in Cscape. First, you're going to select the I/O option that best meets your application requirements. There are 5 different models with different I/O options available for the XLEe. Next, in Cscape, you're going to configure that I/O. Here you need to consider if you need positive logic or negative logic inputs. Do you have high-speed counting? Do you need simple totalizing? Or do you need to interface with encoders and have a quad B type interface? Or do you have high-speed outputs like PWM or frequency, for example? You also need to configure your analog input type. So is it 4 to 20 milliamps, or do you need 0 to 10 volts? Or maybe you have temperature sensors like RTDs and thermocouples that have to be integrated. For your analog outputs, you need to ask if you need any, and if so, do you need 4 to 20 milliamps, 0 to 10 volts, etc. The next step is to configure the network connection that you're using to connect to your PLC or controller. The specifics on the configuration are going to vary depending on which PLC or which controller that the XLEe is being used with from a remote I/O standpoint. Next, you need to write some simple logic, which is mostly move instructions and simple Boolean logic to move your local inputs, both digital and analog, over to areas where they can be available over the network. Then, in the other direction, we'll write some logic to move network commands from the PLC or controller to local outputs. The data coming in from the network needs to be copied over to your local %Q and %AQ type memory locations so that the data ends up turning on and off the digital I/O and setting the analog outputs as is appropriate. Then we'll write some logic that detects any communications lost with the PLC, and then if that occurs, we'll put outputs both digital and analog in a safe state. Finally, you can configure screens with fairly extensive diagnostic information such as I/O status, emulating LEDs, You could display your analog values, or you could have screens for changing the node address, etc. So let's start with our first demonstration, which is our quick and simple setup for getting the XLEe up and running as remote I/O as fast as possible. First, here are some details on this setup. We'll be using the EXLW in both of our demos as the main controller, and we'll use an XLEe Model 6 as our remote I/O block. The XLEe Model 6 has a lot of I/O built into it, which makes it a nice choice. We're also showing the memory locations where each of the 4 different I/O types are mapped in the XLEe, which will come into play later. For this quick setup, we won't be using the XLEe high-speed counter. Now let's head to Cscape. Here's our program that's already created, and we'll walk through how that was done. The first step was to select your model and do the I/O configuration. So we go to the I/O configuration and we've selected Model 6. Then we'll go to the local I/O tab and press Config Module Setup. Then we go through each of the 4 different I/O types and configure it for our own application. In this example, I'm just using positive logic and I'm not using any counters. You would set this to match your requirements for your application, which is true for all 4 of these I/O types. For digital outputs, again, I'm leaving it at the default and I'm not taking advantage of any of the high-speed outputs. For analog inputs, I've set every channel for 4 to 20 milliamps with a filtering level of 4. You can set these to whatever type matches your application. And you can see the Model 6 supports a lot of different sensor types. On the analog output side, I've set everything to 4 to 20 milliamps, and I've set it to go to 0 if the XLEe would ever get out of run mode. So that's my I/O configuration. Next, we need to configure the network that will be used to communicate with your controller. In this case, we have an EXLW as our main controller, and we'll talk to it over CScan. So let's configure that. We'll go back to the controller tab and go to CAN1 and hit config. We need to make sure that network is required because it is in this application. We'll set it to network optimized, which ensures the most efficient transfer of data over the network. Our number of network IDs can remain at 1, but will increase our max packets per scan from 1 to 4. That ensures that regardless of what we need to transmit over the network at any given time, we can transmit all that data every scan of the XLEe. Now we have to configure the network side. With CScan, we do that in ladder. So let's start with a heartbeat. Anytime you're communicating over CScan, it's important that each device on the network generates a heartbeat so that the other devices on the network can detect that they're healthy. We'll put a heartbeat out of our own ID. And I've chosen to use SR29, which is the network ID register, and I'll send that heartbeat out every 50 milliseconds. In addition to sending out a heartbeat when I'm using an XLEe as a remote I/O block, I also want to detect the heartbeat of the main controller. So I'll use a net get heartbeat instruction. Then I'm looking for it from the OCS, which happens to be node 253, and I'll set it that I want to see a heartbeat from the OCS at least every 100 milliseconds. If I do receive a heartbeat on a regular basis, then I'll turn on this coil that I've created called main OCS OK, which is our indicator that the OCS is healthy. If it's not, we'll take steps to make sure our system remains safe, which we'll do later. So that's the network configuration. For local inputs, we need to send those out over the network so that the OCS can use them. And then for the output data that the OCS sends to the XLEe, that needs to be received and copied over to local output registers. Let's start with receiving data over the network and copying them to local output registers, starting with our digital outputs. Here we'll use a net get instruction to take the data from the network that the OCS is sending us and copy it to our local digital outputs. Here we're getting that data from the main OCS, which I have assigned an ID of 253. It's global data and it's set to digital data. This time it's the first digital data the OCS is sending us, so it has an offset of 0. We'll map it in starting at Q1 for 1 word worth of information. So that's where our local digital output data will come from, and this is how we get it mapped to where it needs to go. Similarly, we need to take care of our analog outputs locally. Here we're grabbing data from that same OCS. Here it's set as analog data, And again, it's the first analog data it's sending us, so it has an offset of 0. We're mapping it to our local analog output registers. From the XLEe datasheet, you can see those start at %AQ9 through 12, because we're copying 4 words. Now let's go the other direction, which is sending data from our digital and analog inputs to the network, so that the OCS can use them in its application. So we're going to put data to the network. If we're putting data using our ID, we're sending it to the network under our own ID. So again, I'm using SR29 and we're sending it out as global data. I'm starting with digital data, which is that %I information, and it's the first digital data I'm sending out. There's no offset required, and I'm sending data out starting at %I1 because that's where the digital inputs are coming from with the XLEe. And I'll send it on a change of state. I don't want to send it every scan, only every scan where the data has actually changed. Here you'll also have to choose another bit, which you could use to send additional transmissions. I'm just assigning the always off bit here. Then I'm sending one word of %I information, and that would be %I1 through 16. So that's getting my digital input data to the network. Next, I have to get my analog input data to the network. I don't want to send my analog data on a change of state basis. It's better to send analog data on a periodic basis. So on this rung, I've taken the internal aspect that turns on and off every 100 milliseconds. Then I created a one-shot that I can use to trigger the transmissions of my analog input registers. So it's coming from my own ID. It's analog data, and it's the first analog data I'm sending, so there's no offset required. If you look at the XLEe datasheet for the Model 6, the 6 analog inputs come from %AI33, and I'm sending 6 words because there's 6 analog inputs. The last thing I need to do is to ensure that if the main OCS goes away, that I set my local outputs to a safe level. In my application, I'm saying that is 0. So if we haven't received a heartbeat from our heartbeat rung, then we'll set 0 for Q1 through Q12. It's actually Q1 through Q16, but Q13 through 16 aren't used, so it's okay to copy those 4 extra bits. Then we'll send a 0 to AQ9 through 12, which are the 4 analog outputs local. So that's our programming. The last thing we must do is set up some screens to show local I/O indication. So for that, I'll go to the graphics. Again, this is a simple setup. So for my digital input indication, I'm using a binary data field showing %I1 through 12 as 1s and 0s, and %I1 is right justified and %I12 is left justified. I've added labels here so that users know that it's right to left in terms of indication. I've done the same with Q1 through Q12, which is another binary data field. Finally, for a simple status, I've added the main OCS OK indicator here on the screen. So at a glance, you can see the status of the digital inputs as well as that everything is OK. I've also added a few quick additional screens for displaying the decimal status of my 6 analog inputs and my 4 analog outputs. I also have jump objects for navigating from screen to screen. Next, let's look at the setup on the OCS. So on the right, we have the EXLW, which is the main OCS. In the middle is the XLEe Model 6 that's being used as the remote I/O block. And on the left is an I/O simulator that I have wired to the XLEe so that I can try out the XLEe I/O. As I turn on inputs on my I/O simulator, you can see the inputs turning on from right to left on my XLEe screen and on the right on my EXLW screen. You'll notice that the EXLW is exercising the digital outputs by cycling through them, and you can see that happening both on the I/O simulator as well as the XLEe indication. And if I navigate to my analog input screen, you'll see that as I tweak my analog inputs, it's changing on the XLEe screen and on the EXLW as well. Finally, for the analog outputs, you can see that the EXLW is exercising analog output number 1, and that's showing on the XLEe. Now let's look at a more comprehensive setup for using the XLEe as remote I/O. The basic elements are the same, but we did add high-speed counter support on the XLEe, and we also added an RTD channel. We also made some things configurable on the XLEe instead of being hard-coded like the CAN ID and the CAN ID for the main OCS. We also added some CAN diagnostics and network traffic statistics to the XLEe screen. And we also created some better I/O status screens. So let's open Cscape, and again we'll start with the I/O configuration. We go to the local I/O tab, hit config and then module setup. On the input side I added a quadrature channel, and on the analog side channel 3 is now an RTD sensor. Everything else is the same for I/O configuration. For the network configuration and my program in general, I broke the program up into multiple main loop modules. The first one is our heartbeat handling. This is basically the same as we did in our quick setup, except I made the main OCS ID a register or a variable instead of being hard-coded. In terms of handling the local %q outputs, because I added high-speed counter support, I also need to have at least one clear bit to clear that high-speed counter from the EXLW. In the quick setup, we had 12 digital outputs that were driven by the EXLW but located locally on the XLEe. Then there were 4 extra bits that weren't being used that the EXLW was sending. In this example, because we needed to send a clear bit for the high-speed counter, I tacked those 4 bits onto the 4 previously unused bits. Then instead of copying those directly into Q bits using the netget function, I copied those into local T bits, and then moved the T bits over to the Q bits. That gives me the flexibility of handling these clear bits differently. And the result is the first 12 bits from the network are local outputs, and we have high-speed counter clear bits tacked to the end. So let's look at our local analog outputs. There are no significant changes here. Then, looking at our digital inputs, there's not a lot of change here either. But for the analog input side, I did do things differently. We made the frequency at which we broadcast our analog input data to the network configurable on the XLEe screen in milliseconds between 10 and 100. Then I have logic that takes data and makes sure that it's within limits between 10 and 100. If it's not set, I set it to a default value of 50. Then, here's my netput again, triggered by a variable amount of time between 10 and 100 milliseconds. And I'm sending my 6 channels of analog input. I also have a 2-word accumulator for my high-speed counter. Then I have another netput sending the 32-bit accumulator to the network. The first 6 words of analog data that I'm sending to the network are my 6 analog input channels, but since I'm sending additional information for this net output, I have an offset of 6 because it's not the first 2 words I'm sending, it's the 7th and the 8th. Next, let's look at the graphics. Here we have a menu set up with a main screen, and the user can jump to either status or setup. Let's go to setup first. Here I have the local CAN address which can be set, as well as the OCS's CAN address that can be set. Then here's where I set my analog update rate for my analog input between 10 and 100 milliseconds. Now let's go to our first status screen. Here we can choose between CAN status and I/O status. So let's look at the CAN status. Here we have 4 pieces of information: the main OCS OK status, the CAN OK system bit, and then local system register data for the local traffic being generated by this XLEe and the current total traffic on the network. Now let's look at I/O status. Here we have individual blocks or LEDs for each of the 12 outputs. These screens are more user-friendly, and we added a down arrow on the screen which can be used to navigate. So we have digital in, digital out, analog in for all 6 channels, and analog out for all 4 channels, and our high-speed counter accumulator. So now finally let's look at that on the OCS. Here is our setup, and you can see we have the local CAN ID set to 1 and the OCS CAN ID set to 253. I can use my arrow keys to navigate to my different objects, and I can also use the escape key to return to the previous screen. We can also look at status. Let's look at the CAN status. There we can see our local network traffic we're generating, which is about 4%, and our total network traffic, which is about 8%. So we have fast updates with no significant impact on speed. Now I'll go back to my setup and I'll change my update rate to 25 milliseconds, making it twice as fast. Let's see how that impacts our network traffic. I'll cut to that screen now. And as you can see, we're using more network bandwidth than we were before, but not by a large amount. Now let's check our I/O status screens. So there's the status of our output, and we can see those changing. And here is our analog input values and our analog output value. That concludes our demonstration for today. Thank you for joining me for today's tutorial, and the Q&A session will begin shortly.